Well, let me say what a pleasure it is to be here, at least virtually. So, basic outline here, there's quite a bit we'll try to cover in this hour, but the overall concept is the idea that all models are wrong, but some are useful. So, for every model we present and discuss, somebody will raise their hand and say, that's not quite right. That's okay. What we're trying to come across is what are the useful models for doing overall source modeling. And we're presenting, you're at a workshop where we're presenting many of these different types of software tools. So Brainstorm, M&E, Field Trip, EEG Lab, and there are others out there as well. So the talk is meant to be kind of high level and overview, not specific to any one package. But of course, I can't help myself. I'll be talking about Brainstorm from time to time as well. But generally, everything I discuss, we should be able to find in any of these packages, whether it's commercial from the vendor or one of the many research packages. But I'd like to start off with motivating. This is meant to be kind of an intro class. So I talked to Takfa on how, uh, what the target was here. And I'd like to set up first a motivation. Why do we go from sensor to source space? What are we trying to estimate? And I like to start off with kind of a classic one that, I was always told if when you want to look at your first MEG or EG data is go get median nerve data. So in this case, we stimulated the right median nerve a couple hundred times, averaged it. We see the very classic response of an N20, N30, N45, whether it's N or P, doesn't really matter to an MEG guy, but the classic response is at 20, 30, and 40. There's a little bit of a time shift in this particular instrument, but this is a well-known median nerve response that you'll almost always get, particularly in these first few responses. And if we just look at this data from a sensor level, a sensor map, or a brain map, it's sometimes called in the clinical software, we're just taking these patterns and looking at the pattern it creates, in this case on a flattened helmet. And we see immediately the very classic current dipole problem. So holding your right hand out, diving in, blue is negative and red is positive. You can do your right hand and realize that this one has to be an anterior facing dipole. So you don't even need to do source localization at this point. You're already seeing this is anterior facing. And then for whatever reason, it's fascinating in its own right, 10 milliseconds later, it reverses. Now it's negative and positive. You have a posterior facing dipole. And then a few milliseconds later, again, stays posterior facing. So we have this pattern of anterior, posterior, posterior. And there's actually been quite a bit of work I was surprised to find on trying to understand why some people have this pattern and others don't, what causes these reversals. But this is just an example of the sensor level to a crude source level that you can do with data, but it also sort of sets the stage of what are we going to do with this kind of data. It's also important to note that EEG is always very complementary, and I mean that in the very strict literal sense. It's not redundant or supplementary, it's complementary in that if I have a current dipole here and I have my red and blue, so again, right-hand rule is showing me the correct direction. I see the zero crossing line running in the direction of the dipole. It's a black line here, but a white line here in the mapping. But EEG is always perpendicular to that. We have the zero crossing goes perpendicular to the dipole. We see positivity and negativity, but it's important to note that it's still exactly the same dipolar source. It's no difference in the way we model the current dipole. And they're very complementary directions, and we always run them. This is a very low pattern, 23 versus 306, but you get the point there. And so the basic idea of what we're discussing today is how do we go from this idea from the sensor level data to these maps on the sensor array, whether it be on the scalp itself or at the helmet of the sensor array, and then ultimately to source localization. And the overarching goal is it's very difficult once you get to dozens and hundreds of channels to actually try to make sense of this as compared to say the original EEG data, which was always just 19 to 21 electrodes and mapped it very nicely. As we got to these denser arrays, it really became important to try to map to a different space so we can understand the data better. So let's look at what is an equivalent current dipole. What is a dipole? I like to examine the physics to try to make sure that we understand there's a very real basis going on here, that what we're estimating isn't just sort of fictional or arbitrary values. And so almost inarguably, the number one signal that we're seeing in the cortex is the pyramidal neurons. these long cortical neurons that extend from layer 1 at the top of the peel surface all the way down to the bottom of the gray matter, layers 1 to 6, with the soma usually sitting somewhere in here in layers 4 or 5. And what we're looking at are the postsynaptic potentials that are summed over millions of neurons. We like to draw the single neuron. This is from Ramon Cajal in 1888, his drawing. But we're always looking at the equivalent current dipole at the idea of millions of these. So we're always talking about a microcellular model and not a macrocellular model and not a microcellular. There is a whole other community out there that will argue this at the cellular level. We're always arguing it more at the hundreds of thousands to millions of neurons. And just by the way, Matti Hämäläinen and Dimitris Pantazis, I got a chance to see Ramon Cajal's drawings when MIT had a special hosting of it. It's fascinating to see what he was drawing with shades of gray and ink, back in the 1880s to really detail what was being seen, at that time, new insights into the cortex. If you ever get a chance to see the drawings, they're fun to look at. But basically he sets up this forest of neurons in the gray matter. And here's, from stole off the web, somebody just PowerPoint stamped the same pyramidal cell, but it sets the point of what we're looking for here. We have the soma, we have the dendritic arbor. We're high in the arbor up at the peel surface. We're low in the arbor down basal areas. And the afferents from the other cells in the region are coming in either high in the dendritic arbor or low in the arbor. They usually it breaks down to one measure or the other. And so we have excitation coming in high and excitation coming in low and inhibition coming in low. What do we do with this? What is this excitation inhibition doing? And it's setting up this activity that runs up and down this pyramidal cell. This is why we emphasize the pyramidal cell, because we need these few millimeters running up and down to even see the signal at a distance, as opposed to a stellate cell that just goes in all directions. And so if it's excitatory high in the dendritic arbor, if you put a microelectrode there, you will measure an active negativity. And again, clinical types like to draw negative up and positive down, just like they do left on right, right on left. So they're showing negative up, positive down. So if you had a microelectrode and you had an EPSP in high here, you would see the negativity, and it creates kind of a passive positivity at the bottom, but it pushes, if you will, pushes the current down this dendritic arbor, this dendritic line. If it's inhibition, low in the dendritic arbor, down at the soma, then you have an active positivity, if you will. This has to do with potassiums and sodiums, and there's a whole lot of words around it, but I'm simplifying it as there's an active positivity. And again, if you had a microelectrode there, you would see the positivity. And in this case, it pulls the current down the same column. So these are not passive currents that are just flowing because of a charge. They're actually being pumped down the column here, but we can't tell, is it EPSP or IPSP? We don't know. We'd have to get other knowledge to understand it. We just see that it's flowing down the column. This is all reviewed in these books you see showing on the side. And Kandel, he argues also, and again, I've heard this is arguable, but I like the argument, that if the afferents are coming thalamocortical, so particularly in that median nerve response I just showed, the initial stimulus of the wrist comes up from the thalamus and into area 3B, and it causes an active negativity low in the arbor. So there's the active negativity, and it pumps up the column. And indeed, if you had a electrode on the scalp or even on the cortex, you would see this positivity. And conversely, what he suggests is that most activity high in the tree is contralateral cortical or cortical, and that tends to be in the upper layers, layers 2 and 3, and then comes down the column. So we have this highway of action running up and down these columns, and it kind of sets us up for how we're doing our modeling. So this acts like a little cortical current elemental model. So I'm just looking at these few neurons at the very basic level. I've got my little cortical dipole here. It always has to have currents to complete the circuit. This is basic physics mandates that whatever current leaves this must come back around in. So you have the so-called volume currents or secondary currents. And because of this activity, then it creates the magnetic field, again by the right-hand rule, flowing around it, and it creates positivity and negativity. So we have these EEG and MEG all coming off of a very common model. So how are we going to exploit that? So this is where we come into cortical modeling, looking at the surface meshes and patches. And if we go into a nice, in this case, formalin fixed sample of the post-central gyrus and somatosensory 1, pre-central gyrus, central sulcus here, we can actually literally see the gray mantle on there. And if we look at a 17 now that are coming available, this is in a postmortem one, but you can still, even in vivo, you can see the pyramidal structure, the layers of the cortex. And then right here is where area 3B, so I think this is Brodmann areas, area 3B to 4A to 4 becomes apparent as you with 1, 3B, 3A, 4. As you come around the fundus, you can actually even see the change in tissue. So we're getting quite exquisite in the modern 7Ts. This isn't necessarily true clinically, of really developing this cortical mantle, this cortical ribbon, if you will, at very high resolution. And so it sets us up then to just go ahead and make another wrong model, the cortical column. And so this is classic in physics, where we look at the column of air directly above us, we look at the column of water directly below us, and in this case, we look at the column of neurons directly below 1 square millimeter, looking all the way down from the surface down to the bottom, and we just oversimplify it, saying, I'm only going to consider what's happening at the top surface here. I'm going to consider this as a column. So it's wrong in that we're not really attending very well to the transcolumnar activity going on, but it definitely helps us simplify our interpretation of what is actually a very 3D multi-layer cortex, and instead a 2D cortical surface that we represent in units of square millimeter. So we'll be talking about that quite a bit. How many square millimeters of cortex do you think we're seeing? And then the underlying assumption is, yeah, it's just a compression of everything happening underneath her. So a very useful model to use. And let's just set up then the 2D cortical mantle. We can go everywhere. We can see it very clearly here, but we'll go into the MRIs and pull this out. Set up this cortical mantle, and at each little place in the cortical mantle, just make this little columnar column there and say we have primary current pumping up and down there, and then we put our other boundaries in. But it definitely lets us think in terms of the 2D surface area rather than the true 3D thickness of the cortical mantle. And as I said, it's a wrong model. Dunez was just publishing recently in 2019, reminding us all that many areas are indeed columnar organized. This is the working model we have, but there are other areas of cortex that are not columnar organized. Even as we go from area 3A into area 4, it does not have that nice columnar organization anymore. So whether it's EEG or MEG, it's an oversimplification to say everything is columnar, but again, it's a good working model. So how do we get these surfaces out there? How do we take advantage of this? Well, the surface extraction algorithms that have risen in the last 20 years, 25 years, are doing a phenomenal job these days with even the clinical quality, which can be pretty low quality, let alone the more exquisite research quality. So here's a ECOG for open surgery, craniotomy, where they're putting in a few depth electrodes. We're going to put a grid on there. And so I got from one of my colleagues this picture, and you can see very nicely here the central sulcus and the motor strip. And then this is what BrainSuite rendered. This is about 2011, so this is already over 10 years old that we did this. You see very nicely the cortical surface. Then you see that BrainSuite and FreeSurfer each have a little bit different ways of doing this, but they're doing a pretty good job of pulling out the peel surface and intentionally have differences. This one's a little more, one might say, anemic, but it's good in that sense that it opens it up a little bit to see, whereas BrainSuite's a little more bunched. It's just the way they are finding the peel surface. I remember asking Juan, when you're looking at a craniotomy, how do you know where you are? And he said, look for the knuckle. If you can find the knuckle, there's the knuckle, then that's the motor strip. Once you found the knuckle and motor strip, then you're off and running, the central sulcus, pre-central gyrus, post-central gyrus, you're off and running. And then later I learned if you want to be more erudite, instead of calling it the knuckle, call it the omega. So look for the omega, and you can see the omega here is very nicely represented both in real life and in the renderings here. So it's to say that we get pretty exquisite surface renderings these days of the peel surface of this top of the cortical columns. And we exploit that by the fact that we render surfaces these days as faces and vertices. particularly because of the gamers really coming on board from the last 30 years. Every GPU card now, you give it a list of faces and vertices as a structure, and it'll render you a surface, and it'll render it 120 times a second, and you can race down hallways and bounce bullets off of things and crash cars into walls. So these triangles are where it's at when it comes to rendering a surface. And what we can definitely use are the vertices of the triangle and the face. And what we treat it as is that each vertex is one of these cortical columns. So we say there's a cortical column that we just were talking about, and that the area that it represents is the average of the area of the faces attached to that. And again, we get exquisite linked lists out, so we know exactly what each face is connected to which vertex, each face. Each patch then becomes a collection of vertices connected by their faces. We have a very natural, intuitive, and a physiologic concept of what is a distributed source, a region of vertices on the cortex. And so we're definitely not emphasizing any one cortical column in there, but rather the patch of connected surfaces. So it immediately brought up the question many years ago that we had is, how good is the equivalent current dipole, a single equivalent current dipole at representing this whole patch when it's actually quite undulating, folded, moving in many different directions here. And so we ran this localization of realistic cortical activity. And now if you're a physicist or engineer of my kind of bent, you look at this, you say, well, you just do a multipolar expansion. You drop this into the classic multipoles, and indeed Cream and I wrote anything you'd ever want to know about multipoles back in physics and medicine biology. And it's pretty tedious and pretty abstract. But we dove in anyhow and said, let's go ahead and try applying a dipole plus a quadrupole to these realistic patches. So we generated tens of thousands of patches from 50 square millimeters to 500 square millimeters on not the peel surface. This looks anemic because this is the gray white surface and not the gray CSF surface, but it's the same thing for modeling purposes. Put all those little current dipoles on there, and then fit these extended patches as both an equivalent current dipole and this newfangled dipole plus quadrupole we call a simple multipole. And what we found is with high quality data, so we're putting in very little noise, the goodness of fit slipped from near 100% for this abstract idea of a multipole to just 99% for a dipole, all the way up to 500 square millimeters. Now, if you do real dipole fitting and real modeling, we don't see 1% differences in good of fit. And when we actually looked at the difference in the localization error between where the dipole fit the patch versus the quadrupole fit the patch, we had a 1.5 millimeter improvement. 1.5 millimeter improvement in localization error. We don't have that kind of accuracy in general. So at least clinically, because I work with a lot of epileptologists, when they say, why am I using just a current dipole? Because this is what is used day in, day out for modeling epileptic spikes. You say the current dipole, the equivalent current dipole actually is modeling quite an area of the cortex. You're okay. You can get your work done with the current dipole. So for clinically, at least, we always say, we let them say, just stay with the dipolar models for now. That's what the vendor software emphasizes too. These higher order moments, the parameters of the quadrupole or of the patch, however you might describe it, are just not strong enough to be worth particularly a clinical time to pull out. Doesn't mean for research you shouldn't go after it, but at least for clinically, modeling patches as equivalent current dipoles is more than adequate. But it still begs the question, as I mentioned, we get current dipoles all the time out in evoke studies, that median nerve dipole and epileptic spikes. What does it mean? I mentioned it's probably millions of neurons. How do we know this? And in evoked in average studies is typical when you do like that median nerve to come up with a dipole amplitude of about 20 nanoamp meter. It's kind of an unusual unit, but it's just the amps times the distance. And in modeling ventricular spikes, we generally see things 10 times stronger. And indeed, we train the fellows that if you see a spike much less than 100, it may not be epileptic, it may be normal. It's getting in the range of normal stuff. So we're looking for abnormal amplitudes versus normal amplitudes. But what can we infer about these amplitudes? And so if we go back to the original modeling that Matti and the other Finns did in the 93 paper, they came up even at that time that the pyramidal cell was thought to generate about a 20 femtoamp meter signal, one single cell. This was based on the basic finite element models at the time, and they're not differing much more than a factor of 10 these days. But what that means physically is we think it's about 10 picoamps flowing along the 2 millimeter length of this, or if its electrical length is 1 millimeter, it'd be 20 picoamps, but something 10, 20 picoamps. But we're seeing nanoamps, so nano, pico, femto. So it means we're looking at 1 million cells when we're looking at our 20 nanoamp meter, or rather 20 microamps flowing through 1 millimeter. So this is what set the stage even at that time to say it must be 1 million cells we're looking at. And epilepsy is just a 10 times stronger, and for reasons it's probably a much larger source. May also be because it's dysplastic cortex, so it creates something a bit more unusual than the normal cortex. Now, if you do any kind of functional stimulation, like these days, deep brain stimulation is becoming quite popular for more than just epilepsy, but also for Parkinson's, motor movement disorders, and now even depression and obsessive compulsive disorders. Those stimulations, at least in epilepsy, we're usually putting about 4 milliamps into two contacts 5 millimeters apart. So that's 4 times 5, that's 20 milliamp meter. That means we're doing deep brain stimulation. We're doing exogenous stimulations of 20,000 nanoamp meters. So again, sets the scale for what does deep brain stimulation and other kinds of stimulation doing relative to what endogenously the brain is generating when it creates an evoked response or has an epileptic spike. There's order of 100 to 1,000 here between these. So it brings around the question, though, all right, we're back to our cortical columns. How much can 1 square millimeter of cortex generate? And indeed, Yoshio Okada has spent his career carefully measuring this in a variety of species. There's other publications that support it as well, too, going back to the 70s. But over his years, he looked at the rat cortex, the swine, monkey, 2 SEEG patients that were in the monitoring units of a hospital, turtle cerebellum, and guinea pig hippocampus. And these are oftentimes craniotomies. He's right down on top of the sources, and he was able to work out that there seems to be an invariance across species that generally, in terms of nanoamp meter per square millimeter, you see that's kind of an unusual thing. You might be tempted immediately to try to divide out the meters. No, leave it in this unit. This is why we're doing this cortical columns. How many nanoamp meters per square millimeter can you generate? And he's finding it's about 1. This rat was getting as high as 2, but the SEG patients are a half. But if you just blur your eyes and look, we're in the category of 1 nanoamp meter per square millimeter. So that sets the stage for interpretation because, excuse me, as we mentioned, we're looking at 20 nanoamp meter and evoked responses. So that means there must be a minimum of 20 square millimeters of activated cortex generating that signal. It can't be one of these little small individual columns. It's got to be something at least 20 square millimeters. And remember, the humans are putting out more like even epilepsy patients, half. So I mean, this is 40 nanoamp meter instead of 20 nanoamp meter. You can see simply by varying this current density, what you think the actual density range is from 0.1 to 1, you can easily change these numbers by a factor of 10. But it just drives home the sort of uncertain nature we have of what is the actual current density and how large are these sources. But when we're doing evoked responses, particularly doing epilepsy responses, we're definitely seeing quite large areas of cortex, and yet we routinely fit current dipoles to these. Very consistent with the study we did showing up to 500 square millimeters still looks like a current dipole. So we've got our understanding, our physiology, we got current dipoles. Let's go model it. Let's do some source estimation. Well, the first thing we got to do is figure out where are the sensors with respect to the subject. And so most of the instruments we've had in MEG have always come with this thing called the isotrack system, where you have a reference sensor and another one on the back of the chair, and you can pretty accurately, according to the vendor, get millimeter precision as to exactly where each EEG electrode is and where each fiducial, usually nasion and preauriculars are. You have to be careful using this isotrack system. Michael Funk and I wrote this article a few years ago towards best practices. where we teach this in the AC Megs course too, how to do this right, because you can do it wrong so many ways. And indeed, Anso and I worked on this for quite a while, finally realized she was able to reverse engineer. It was the way we were holding the pen and the wires and everything. We were really getting bad mislocalization. So she did a bang up job of figuring out how this system actually works. Was quite her contribution. But, that's almost 40-year-old technology. These days, 3D scanning is popping up everywhere because of the 3D printers. So we went out and grabbed one of these devices and are doing now implementing the 3D scanning for registration. We found Robert Usneveld very nicely already had extended routines and field trip for, I forget the name of his 3D scanner. We took those routines and extended them for the one that we went out and bought. And so we're pretty close in development and brainstorm to releasing this, where you can use these pretty easy to use 3D scanners, just run around the subject. Now you have a nice recording of where all the electrodes were, where they looked, and you get all the locations almost auto labeled, even now with some of the software working on. And then of course, everybody wants to know, how does it compare to IsoTrack? Our in-house studies that we haven't published just yet show we got about 2 millimeter difference between what we see between what the 3D scanners are showing versus what the IsoTrack scanner is showing. These devices cost like less than $1,000. They're almost several hundred, whereas that little pin right there is already $800 alone, and you drop that all the time and break it. So we're pretty excited to get away from that very expensive IsoTrack system and use what appears to be a far more accurate and easier to use system. But the real goal is to get the landmarks of the scalp, because once you have the landmarks of the scalp and you know where the EEG electrodes are, and you know where the fiducials are, nasion, preauriculars, then you can do a fit the cap. And the research softwares, in Brainstorm and M&E, I'm not too familiar with the other ones, but there's a button you can click, and you take all those points you collect by the system and you get them to fit the scalp of your MRI. And once you've got that, then you know where all the fiducials are, you know where all the landmarks are, and more importantly, you know where all the sensors are now. So for EEG, they're on the scalp. For MEG, they're in this helmet outside there, and OPM is still working out this issue too. Where are the sensors with respect to the cortex? It's important you get this accurate registration so that you can get, in turn, get accurate location of the sensors. Both M&E and Brainstorm use exactly the same coil definition file, so we both model the MEG coils the same way for all the systems, including OPM. We share a common definitions file. So the key is getting good landmark registration done up front, and then we're off and running with the modeling. We know where all the sensors are, we know where the channels are, we know where the cortex are. We're ready to start setting up the forward model. And EEG is always recommended, again, particularly UT Health and elsewhere. We always just collect the EEG. We don't necessarily try to model so few channels, but it definitely helps exploit the complementary pattern of MEG and EEG. And sometimes we find sources in one that we don't see in the other. But that sets us up now. We're ready to do the forward modeling. So what's with forward modeling? What are the kind of forward models we find in these packages? And so the basic problem is we have our cortical column, in this case, like a little battery, and it's somewhere in a conducting volume, and it's cranking out volume currents. And so these volume currents set up potentials on the surfaces and set up magnetic fields outside the head. We really don't care about the volume currents, but they are absolutely essential in creating the total data. They're just gradient currents. They complete the circuit. And the best way to define what primary is it's not the secondary. We want our models that are in terms of just primary so we can get back to business and forget about that. And so that's a solvable problem. It's technically difficult, but every current dipole location you might put in the brain, there is a unique EEG or MEG sensor solution as to what a sensor would see outside the head. And it's this boundaries that are shaping all the problems. So mathematically in the forward problem, we synthetically say, what if I had a 1 amp meter, that's just for normalization purposes, dipole at this location with this orientation, what would be the gain vector out to, in this case, 7 sensors? We create that into a little gain vector. And then from that, we have to solve things like the Biot-Savart law. We're looking at the total current flowing out to the sensors. But it's quasi-static electromagnetics, and they say we emphasize primary rather than volume. And if it's a spherical head, there's a well-known, it's been around for decades now, closed form for if you specify the primary dipole, we'll give you the gain vectors. Pretty easy, but it is for a spherical head. more realistically, and what really sells to committees, to grant reviews, to papers, they love to see these boundary elements and finite elements. These are harder to solve, but they look far more realistic. But it's still the same problem. Given this 1 amp-meter dipole, now the basic fundamental model is there's a quasi-static assumption that the divergence of these gradient fields times their conductivity is equal to the divergence of the primary activity. This basic fundamental model gets worked again and again and again across all boundaries, scalp, inner skull, cortical surface, or finite elements, tetrahedra, that are in the brain, CSF, scalp, anywhere you want. The ultimate question is what produced the gain out to the sensor G. And so this is what's worked by all these packages. Every one of these will have some form of building you a head model. You have to get good isotrack or localization and get good registration. But once you give it the sensor locations, registration, and pick a model, it's off and running with solving in one way or another this basic equation. So in Brainstorm, we have the basic ensemble of it. We have this spherical head, and you can see single sphere fit to the head. It's usually just doesn't look very good. It's quick though, and this is what was used for decades before we got these better renderings. But once the MRIs came around and we were able to use those better, then what we developed was overlapping spheres, where every sensor gets a unique sphere, not one sphere for the head, but every sensor gets a unique sphere fitted to that sensor in the head. And we found in practice that that's generally sufficient, particularly for clinical work or just to get the job done. It's also an analytic solution, but more realistic. And again, if you're writing a grant to committee, they love to see these things. You get this beautiful tessellated surfaces, and usually in boundary elements, you're only interested in the boundary, literally, between the things. We usually work with the inner skull, the outer skull, and the scalp, and you assume isotropic conductivity throughout the space. But again, it's a solvable problem through boundary element methods, or more recently now, people have been working very hard on finite elements. So this is the OpenMeag software. The OpenMeag software is a boundary element that M&E and Alexander Gramport developed. And then we have the FEM that Takva wrote a very nice article on recently, using Dune Neuro and inside of Brainstorm to handle this more realistic looking tetrahedra that you can assign multiple classes of white, gray, CSF, skull, scalp, and you can go in the anisotropic world. You can use DWI, DTI to say each little finite element now actually has preferred current direction. So quite realistic head modeling. The question you always have is, this takes you a few seconds, this can take you hours, this can take you many hours to generate. How much time have you got, and how much precision do you want? And then by electromagnetic superposition, once you've done it for one, then you know it for all. Because if you want to do multiple dipoles, then it's just by electromagnetic superposition, you just literally just sum them up. There's no other thing to do it other just sum up the gain for your A dipole, your B dipole, your B, using the actual signal strengths once you've built these up, and mathematically represent that as the sum of P sources with their source strength, nanoamp meters, plus the ever-present ubiquitous concept of noise. So let's make push. The early picture I showed was only like 15,000 triangles. These days, we have the memory, we have the space. We can work with the renderings that come right off of FreeSurfer, Brain Suite, and the others now, Cat12. When you run a adult human brain through of a reasonable quality, this is not unusual here. We get, in this case, 270,000 vertices, so exquisite vertices, 538,000 faces connecting this. This is a feature of topology here that usually the faces is twice the vertices, so it's nearly a perfect surface. And then also we find as we're spanning, because these are triangles, are beautiful to ask these questions, spanning about 200 square centimeters or 200,000 square millimeters of cortex. As a working number, the adult human brain spans 250,000 square millimeters. That's to say a quarter square meter. That's just kind of a working number. And here's an actual case where, came in close enough for government work. 252,000 vertices spanning 200,000 square millimeters, all nicely labeled as to precentral gyrus, postcentral gyrus, angular gyrus, superior temporal, all nicely labeled and ready to run. And oops, went too far. And we can go into each vertex now. Because it's about 1-to-1, each vertex of each triangle represents about 1 square millimeter. So this is beautiful for our assumptions, what we think is happening in the modeling. And we can also, for simplicity in this presentation particularly, we can go ahead and restrict our dipole model to be normal to this rich cortical surface. So we're not going to do unconstrained dipole modeling, at least in this talk today. And so if we do Lie field analysis, let's assume this particular source, we have about 270,000 vertices, and let's assume we have about 250 sensors or channels of data coming in, EEG, MEG, OPM, however you want to do it. And for each of these vertices, we calculate the forward model to all the contacts using, like, say, OpenMe for boundary element, Dune Neuro for finite element. And we calculated each of the X, Y, and Z directions. So that gives us a gain matrix for each dipole that's 250 by 3. We pack those all together to give us a Lie field matrix of 250 by 810,000. But that's only a few gigabyte at single precision these days. So that's very manageable in our systems. Probably not on the laptops that you're carrying around, but it's getting actually better. My laptop tends to die when I put this stuff in, but my desktop handles this just fine. And this Lie field matrix, then every 3 columns of it is the gain matrix for a single dipole somewhere in your headspace. And by reciprocity, each row of this matrix represents samples of the Lie field for that channel. It does solve the transcranial magnetic stimulation or transcranial electric stimulation problem. It is the literal embodiment of TES or TMS when you look at the rows of this matrix, and like I say, the columns are the gain matrix for each of the dipoles coming out. So it's a very useful to build this beautiful Lie field matrix. And again, each of the software packages will build you that. So what do we do with that? Well, we make this massive model then. As I mentioned, it's in this case 270,000 dipole matrices, and they're each one's a little 3 by 3. And I build a source vector of 270,000 vector dipoles, each one itself 3-dimensional, and I have additive noise. So once we make this as our sort of our measurement model, we're assuming somewhere in these sources going out through this Lie field, we're making our measurements. The 2 main approaches, and there's all kinds of ways to do this, but this is what we're doing this morning, is to either do dipole modeling, in which we ask which of the few columns of L fit the measurements, versus source imaging, what collection of patches over all the columns of L fit the measurements. So either a few or all. This breaks down as to dipole modeling versus source imaging. And to keep it simple, like I mentioned, let's not use matrices. Let's go ahead and use those normal orientation of each one of those dipoles in their constrained orientation normal cortex. Then it becomes 270,000 columns for 270,000 dipoles and 270,000 scalar amplitudes, so that the orientation as a free parameter is out of the discussion for today, but it is something that will pop up quite a bit. Now, you have to design, you don't measure, you don't estimate, you design a source covariance. It's the expected value of this JJ transpose. This is a 270,000 by 270,000 matrix. It's enormous. And it's basically, I mean, you're designing it. So almost everybody, in our software at least, just designs it as diagonal. I need to set a expected design covariance for each and every one of the diagonal elements. And typically we do it as inverse to depth. There's lots of other variations that exist. We won't discuss it today, but this just sets up a design source covariance that's necessary to complete the modeling. And then what's actually crucial though in all of it is you need a noise or baseline covariance. This is where sometimes people race forward through it too much. You need to decide what is the expected value of the noise. And from this, typically you get this if it's MEG from empty room. But if you're doing EEG, what's an empty room in EEG? There's no measurement until you put the cap on. And even in MEG, there's arguments like empty room's a little too empty. You need to go find some baseline brain activity that's void of the signal of interest. Now, thankfully, fMRI has designed a whole host of protocols which can also say this brain activity looking at is our baseline. But you specify or estimate this covariance of n transpose. And when you're processing data, make sure you move the mean, because we're assuming 0 mean on there. And then we can ask the question then, what estimate of j hat minimizes this squared error, so j minus j hat, given that, and this is crucial, given that the estimator is linear. We want a linear estimator, want some sort of linear weights applied to the data Here's the data. This is my linear weights. What will be the optimal solution? You can write it out almost directly. It's just well known. It's the Wiener filter. We also call it the weighted regularized minimum norm estimate because that's the way it was developed in the MEG field, or you know it in M&E Python and some of the codes is simply M&E, now minimum norm estimate, but you give specifications for the source covariance and noise covariance inside the model. Now, back to the dipole model, I can hold everything exactly the same and say, now I'm going to just pull out some unknown small set of dipoles, a small set of fixed orientation dipoles in there, 5, 10, not many. But we make that matrix called A. And so my model now is just AX plus N. I put these handful of dipole amplitudes into X. I put these handful of vectors into A. I'm just changing notation. And I pull out the corresponding design covariance CX. The answer still remains exactly the same for LMMSE. The Wiener filter solution for that is this. But by matrix inversion lemma, because it's a tall matrix, we can identically write it this way. So these two equations are exactly the Wiener filter, and they're just the exact same thing for a min norm, but just done for a few, at this point, unknown dipole location. But once you have a dipole location set, this is how you solve for the moments. Now, because it's tall, it allows us to send the source covariance, the design source covariance, you can drive it to infinity. If I drive this to infinity, its inverse goes to 0, so this goes to this. And when I drop that back into the answer, you answer a different question. You get the best linear unbiased estimate for a dipole moment called the blue, where it's structurally just missing this component in it. And the advantage of blue then is you don't need a source prior. But the disadvantages are we oftentimes end up putting a source prior in anyhow to regularize it, ticking off regularizers. And we still haven't figured out how to find the small set of dipoles. This is what's called dipole fitting or dipole hunting out there for that. And then the other thing that's popped up in the last 20 years is these measures themselves directly, these estimates, are a little unstable because of all these uncertainties in there. So what popped up, particularly with DSPM in 2000 with Anders Dalla, was to let's take that ith dipole deep in there, whether it's 270,000 or 5, and there is just a set of linear weights that's being applied to the measurement data because we're always just looking at what's being applied to measurement data. So now we're looking at the ith row of our estimator going into the measurement. It creates our ith estimate, and we apply that to the noise covariance. That's why it's important you get a good noise covariance because you're going to use it in this manner. If I apply that same weight to the noise covariance, then I get a DSPM weighted score that's this estimate divided by that noise, that estimator noise, and this is called a DSPM or a Z-score based on the noise. And S. Loretta came out in 2000, one right behind it. Pascal had a different concept, but same scaling. He applied it not to the noise covariance, but rather to the data model. Not the data covariance, but the data model. And so this sets up DSPM and S. Loretta, which you'll find a lot of package people say, I want to do DSPM or S. Loretta. What's important to know is DSPM and S. Loretta are min norms. They are the min norm, but then they're scaled by these different scalar factors to make them more usable. And so beamformers is the other one that keeps popping up. If we go back to the blue, recall that it comprises a few dipoles in unknown locations. I still haven't told you how to find those. But if we have an estimate of the data covariance, not the model, but the estimate of data covariance estimated straight from the data, then we can scan for a few dipoles using the single vector dipole model and replace the noise covariance with the data covariance to yield what is known as the LCMV, linear constraint minimum variance, or the MVDR, minimum variant distortionless response. Out in the beamformer community, they call this the Capone estimator because Capone actually came up with this in 1969. But it's a very simple model, and when scanned or imaged over all of the dipoles underneath the right conditions, it will peak at the right locations on a small set of dipoles. So you get a nice set of peaks in your beamformer output. And it also has something called the neural activity index. You again can divide this by applying that same weight to your noise matrix. So there's an analogous score of neural activity and beamformer output. So this Caroline Witten a few years ago got us all together in a room, the Python field trip, SPM 12 brainstorm, locked us in a room almost literally for a week. Wonderful accommodations, but we were all stuck together trying to show how our beamformers worked with her data, and the Meet JSWAL was the test case. So we all ran our beamformer implementations because there's devil in the details with the beamformer. The min norms are actually more alike than different, but the beamformers we were finding were pretty different. And so we compared all of our beamformers against the same data set and published it in this comparison. And we discussed the critical differences between implementations. And then Britta Westner, 2 years later, got us back together to write a unified view on these to get a unification of terminology and comparison implementations. So there's a nice table in there trying to explain how each software package addresses the problem of how to do beamformers. And the variations I haven't discussed are these estimators. Clearly, I picked one way of presenting to you how the estimators developed. There's lots of ways to do it. I glossed over the math of the orientation constraint because it makes things simpler if you do scalar. There are variations of source covariance time that are not necessarily diagonal. The original Loretta, not to be confused with S Loretta, but Loretta and Everetta, I forget all the ones, Lara. Yeah, there's a lot of other ways you can do source covariance designs for min norms. And the music method also does not require inverting. It is a beamform, but it doesn't require inverting the data covariance. It rather uses a signal subspace. And in Brainstorm's dipole scan that you can run in there, it's actually a music implementation. There's also the choice of, do you want to look over the volume of the brain? Because min norms can be done over the volume. This is the min norm image of a single sensor outside the head looking across the entire volume. But a design choice is, do you look over the volume of everything or to look over just the cortex, restrict yourself to cortex. So that, again, is a design choice that goes more to interpreting the data than it does for anything actually physical. And if we look at solutions, these are out of Brainstorm. This is doing an M&E with the orientation constrained at every dipole. This is where we actually left them unconstrained. You know, as I said, I didn't discuss how we do that. And then this is through the volume unconstrained. So rather than looking cortical surface, looking through the volume. This is DSPM done through it and S Loretta done through it. If you fuzz your eyes, you realize these are far more alike than they are different. People argue quite a bit of the subtleties of this, but actually these are far more alike than they are different. A separate study we did several years ago now was we were able to go to MGH, to University of Minnesota, and to University of Mexico, where they had the Neuromag, the CTF, and the BTI, or the 4D. And so we ran the same subjects over many months, repeating them across there, and then we ran the DSPM estimates through M&E, then we ran the DSPM estimates through Brainstorm. We noticed there's a bit of an angle difference here, but a bit of a shift in the answers. We found we had a little bit differences in the way we were deciding what the coordinate systems were, but indeed it was at that time that Brainstorm and M&E then were on joint grants for the next 8 years. We had the exact same grant to bring our two packages together. And so we published this data also. So I've got, it's already about now 10, but I can keep going for a few more minutes. I know we were late starting. I got a thumbs up, good. So how do we know all this works? Phantoms. Phantoms are a great way because the human condition is complex. Heads aren't spheres, sources aren't single dipoles. And so this is one of the calibration phantoms that comes with some of the vendors. You just pump current up a twisted pair, so it's mostly magnetically silent. And then the current runs out and back in. One of our early experiments we did at USC, we put electrodes on the inside of the sphere. So you can measure the EEG, but you can also definitely measure the MEG. It's wet though, it's got saline, it gets an air bubble. Easier to work with in the lab are dry electrodes. These are little loops of wire that we use at Los Alamos to calibrate our novel prototype we built. And then this is what comes with every Neuromag one. It's usually hidden by a plastic shell now. Little triangular dipoles. They're just little pieces of wire. Again, no mess, no fuss. And we can usually get sub-millimeter accuracy on localizing exactly where these sources are. So that's how we know the instruments, the physics, everything's working together. We also built a human skull phantom several years ago now, painted 40 layers of conducting latex onto it, and then filled it with conducting gelatin, no sugar because it'll rot, but just conducting gelatin, and then built an entire electronics array to go into there and wired it up with EEG electrodes and gave it 32 optically isolated current dipole sources, and then got a CT of it to find out exactly where these sources ended up. Ran it at night in the neuromag because you don't want to freak out the patients during the day. And then even ran it on the early version of the EGI hairnet at that time. What we found is there was one errant MEG dipole that was stuck behind the eye socket. But in general, MEG is the green one here. The dipole localization was always substantially better. There was an area where they were alike, but other areas were substantially better. Indeed, usually about 2 times greater. And we were also able to test out a lot of these 4 models. We used the spherical model, the overlapping spheres, a realistic boundary element. We averaged errors, and we found generally about 4 millimeter error for MEG and 8 millimeter error for EEG, regardless of what type of technique we used. And so we dug in trying to understand, why does EEG have this problem? And if you look at our skull phantom, you'll see this is what still bedevils us today for EEG. It's this true human skull. We typically still, even today, model the human skull as one homogeneous boundary, but in reality, you've got sutures running up through. This is the diploic space that has the same liquors of the brain that are in the brain itself, so highly conductive. So you've got highly resistive, highly conductive, highly resistive, highly conductive. These are like 80-to-1 conductivities, maybe 40-to-1. It doesn't really matter at that level. And then you've got temples where there are no diploic space. The modeling of the skull is still today a bit of a nightmare. We need millimeter-sized triangles, and we're still just not quite there. And this is for a normal head. You do a patient that's holes drilled, and now you got breaks and burrs and holes in there. So our supposition is the imprecision of the modeling of the diploic space, and that's still a problem today. So wrapping up, then, you've got all these nice software tools for MEG and EEG. You're studying several of them now in the afternoon on the workshops, and they all tend to follow this basic workflow. This is listed as brainstorm, but it's generic. You can always just start with raw EEG image data. You saw at the very beginning, all we did was go straight to analysis. We looked at the sensor pattern. We could do averaging. We can do all kinds of things with time, frequency, connectivity stuff. It's been done for decades right off of the machine. And indeed, some of the OPM systems coming out right now don't have the sensor locations yet. So they're right here, still doing this part of analysis. Once you have good sensor locations, good registration, good anatomy, you can now do accurate co-registration. Once you have the co-registration, you can get a beautiful lead field model. And once you have this lead field, this very physical lead field model, now you can do source estimation. Once you have the source estimation, you're off and running again with time series. That'll be the point of this afternoon's talk in source estimation part 2. What do you do with the time series coming off of all these sources that you have? So in summary, it all rests on this basic, simple, quasi-static model. I put the time dependency here again. We have these sources coming through what's called a lead field model that converts amp meters to Tesla or volts, and you have this ever-present noise. Everything downstream depends on whether or not you have a credible lead field model for how this is translating, and some sort of sane noise covariance. You really need to get noise covariance done nicely. Biophysics sets the intuition. We know about what an equivalent current dipole is now. When we get an ECD out or have them on the cortex, we've got a pretty good idea what they're representing. And this Okada constant lets us do even back of the envelope areas from the moments that we see. And cortex modeling matters. We can take these realistic, highly dense 3-dimensional surfaces and reduce it down to a 2D mantle that matches physiology. Co-registration is very important. You've got to get the registration right. We see a number of times where the co-registration is just wrong, and then we can't use the data. But the forward models are your design choice. You have to decide really what you can tolerate, both in the complexity, simplicity, and time. Spheres are fast and often fine for MEG. Once you get over the lack of acceptance of a sphere, because it's not a great change of boundary, you say I model as a sphere, but the calculation of the computational electromagnetics is precise. The models are, or the answers are known. Boundary element proves some of the realism, but you've got to get those triangles right. Triangles can't touch, and got to keep enough separation, and the computational EM of that is itself problematic. And the finite element handles anisotropy when you need it. This is still, under study. Can we show when do you really need the complexity of FEM versus BEM? Once you have this forward model set, though, then the inverse models in practice are the dipole fitter scan for focal high SNR events like in epilepsy. And then the M&E plus its weightings, DSPMS Loretta, helps handle these more sort of ongoing movies of dynamic activity. And then people are always trying out the beamformers for the spatial filtering, but you really got to put a lot of care into the covariance, data covariance, what windowing using the data, the regularization are all pretty important. That's what those papers were about. And our phantom results, though, show that MEG spheres can be acceptable. BEMs help reduce some of the error, was a great improvement. EEG is a little bit worse, probably because of the skull uncertainty. So that's my pitch for source level analysis part 1. Thank you.
Once again, thank you so much, John.
Yeah, my pleasure. Thank you.